There's something here that you can't see, something invisible, that makes a scene like this look ordinary every day. Something that, if you took it away, it would be a disaster. What would happen if you took away the air? Firstly, the sky would no longer be blue. You would look straight out on the black sky of space, even during the day. Secondly, the sun would start to burn you on one side while you froze on the other. Oceans and lakes would boil. Any fires would go out immediately. Aircraft could not fly. But you would have only about 30 seconds to see it all before you passed out, and in 7 to 9 minutes, you'd be dead. We need air to live, and if we don't get it, we die. Something in air keeps us alive. Whatever it is, we use it up, because in a closed space we can only live for a limited time. This life-giving air also keeps a candle burning. But not forever. Eventually, the flame dies, having used up whatever it was in the air that it needed. But what that was remained a mystery for centuries. But finally, chemists identified the ingredients of air. They called the life-giving burning gas oxygen, and almost all the rest turned out to be a gas they called nitrogen. There are also small amounts of other gases, one of which was actually increased when things burned or breathed: carbon dioxide. Like flames, all animals use oxygen and produce carbon dioxide. Only plants are capable of reversing this process using the energy of sunlight. The process of photosynthesis in plants has enabled the Earth to gain an atmosphere rich in oxygen and low in carbon dioxide. Plant life, both on land and in the sea, using the energy of sunlight, creates an atmosphere that supports all living things. Life has created its own atmosphere over millions of years. But apart from allowing us to breathe and stay alive, how else does the atmosphere affect us? The atmosphere lights up the sky so that day looks totally different to night. At night, we look straight out into space. But in the day, sunlight is scattered by molecules and particles of the atmosphere. Most scattered is blue light, so the sky looks blue. And of course, the sea reflects the sky. At sunset, the sun looks red because its light has to travel through much more atmosphere to reach us. And by then, most of the blue has been scattered away. Only the red end of the spectrum is left. So the atmosphere changes the way we see our world, and it supports our life. It also allows us to fly. Every time we fly in a plane, we rely upon the air flowing over the wings to lift us up. We also rely on oxygen to burn with the fuel in the engines. Only rockets, which carry their own oxygen with their fuel, and which are so powerful that they don't need wings, can fly without the aid of the atmosphere. Balloons, ironically, rely on the weight and density of the atmosphere to get up. By being filled with hot air or some other gas less dense than air, they can float up, just like a submerged object less dense than water floats up. So the balloon relies upon the fact that the atmosphere has density and weight to provide it with a substance to float in. And the atmosphere does have considerable weight. On the ground, at the bottom, it presses down with its greatest force, and being all around, it presses in on all sides. It can easily crush a metal can if the air inside is removed. In fact, the weight of a thin column of air, 1 centimetre by 1 centimetre, reaching up all the way to space, is approximately 1 kilogram. So it presses in on all sides with this force of 1 kilogram for every square centimetre. The exact weight varies with the weather, increasing a little in a high-pressure cell in fine weather and reducing a little in stormy weather. While stormy weather may be inconvenient, it's another aspect of the atmosphere that's also vital to us, especially in a drier country like Australia. We need rain, which arrives in the form of clouds. Clouds are made up of millions of water droplets. Warm air can carry water vapour, and as it rises, it cools. Water droplets form around particles of dust, smoke, or salt from evaporated sea spray and create clouds. We then want the wind to blow them over the land so we can have the rain. There are two main causes of wind and weather generally. They are the heat of the sun and the turning of the earth. On average, the hottest part of the earth is the equator, because there the sun is directly overhead. As the air at the equator heats up, it rises, and cooler air flows in along the ground from north and south to replace it. Also, on a rotating Earth, the equator goes around faster than anywhere else on the globe. So the air coming in from north or south will be moving slower than the equator. As it gradually catches up, it seems to blow from the east. These are the trade winds. And where does the warm air from the equator go? It flows outwards, north and south, higher up. As it cools at high altitude, it descends to create a belt of cooler westerly winds. Thus, a basic worldwide pattern of winds is created. Wind, weather, and ocean currents transfer the sun's heat around our planet. The atmosphere and the oceans save us from being alternately barbecued and deep frozen every day as the Earth turns in space. By comparison, temperatures on the Moon, which has no atmosphere, go from plus 100 degrees C during the day to minus 150 degrees C at night. Life on the Moon would be impossible without thermal protection, such as the atmosphere gives us naturally on Earth. And not only heat. The sun emits a dangerous level of ultraviolet radiation too. Fortunately, much of it is absorbed by ozone, a 3-atom form of oxygen, which is present in the upper atmosphere. Unfortunately, ozone is a delicate molecule, easily destroyed by CFC gases. CFC gases were created by humans for use in fridges and spray cans. When it was realised that escaping CFCs were reducing our natural ultraviolet protection in the atmosphere, a big effort was made to stop using them. Humans have affected the atmosphere in another important way. Cars, factories, and even wood fires in thousands of villages have raised the level of carbon dioxide in the atmosphere, not to mention certain other gases too. These so-called greenhouse gases absorb some of the heat released as the sun shines on the Earth's surface. This effect is normal, as we've already mentioned, but as greenhouse gases increase, the atmosphere will tend to trap more heat than usual. This is called the greenhouse effect and is creating some concern.
It certainly is creating concern. As levels of greenhouse gases like carbon dioxide rise, the world's weather is likely to change. And when the world's weather changes, that's likely to have lots of effects on agriculture, even on natural systems. At CSIRO, we're taking a special interest in trying to work out exactly how the greenhouse effect is going to make an impact on Australia and on the rest of the world as well.
Paul Holper is part of a team at CSIRO Division of Atmospheric Research based in Melbourne. They're studying the composition of the Earth's atmosphere, going back 1,000 years or more.
At a place called Cape Grim in northwestern Tasmania, a very isolated laboratory, we have been collecting air every day for the past 20 years. We analyse it to find out what's happening to the atmosphere. We can go back, though, even further in time and look at air that's trapped in Antarctic ice. That tells us about the changing atmosphere, the changing makeup of the air for thousands of years in the past. As snow falls in Antarctica, every so often it traps a little pocket of air, more snow falls on top, and eventually that snow turns into ice. So we have ice with air trapped inside it, and if you drill down into Antarctica, the deeper you drill, the older the air that's trapped within the ice. We drill ice cores and we bring them back to Australia, and then in a laboratory we release the air from the ice and analyse that air to find out exactly what the atmosphere was like thousands of years ago. We found out that in the past the atmosphere has sometimes contained high levels of greenhouse gases and at other times lower levels of greenhouse gases. At times when there were high levels of greenhouse gases, the world was warm, and at times when it was low, there were usually ice ages when average temperatures were fairly cold. In recent times, levels of greenhouse gases, including carbon dioxide, have been very high, higher in fact than we've experienced during the past 160,000 years. The concern is that if greenhouse gases continue to rise, the world's weather and climate will change, and if the world's weather and climate change, the impacts are likely to be quite widespread, both on Australia and the rest of the world.
So the atmosphere is changing, getting warmer. While it's a good thing that it protects us from the cold of space, there are reasons why we wouldn't want it to get too hot. There's just a single example. Water expands when heated, so we expect a rise in sea level. What other changes might we expect from the greenhouse effect, and how will it change our lives? Can we do anything about it? Only time will tell.